Yeah. So the first question is the phase velocity of a wave of frequency 194 terahertz and a wavelength of 1.55 micrometer is how much? So phase velocity we know is Vp is nothing but what is phase velocity? Omega over lambda, right? Or in this case, since they have given us the frequency, we can write it as lambda into nu. So that is 194 terahertz means 10 power 12 into 1.55 micrometer means 10 power minus 6. That is 3.007 into 10 power 8 meters per second. So this was easy. Next question. Find the velocity of wave packet if omega is so much for k equal to 1.5. Okay. So they have given omega as a function of k. And they are asking us the velocity of the wave packet. So we know that velocity of wave packet is del omega by del k, right? From here we have to get the velocity. So we need to differentiate omega with respect to k. So this will be nothing but 1 minus, this is 0, 1 minus 2k plus 3k square. Now we just need to substitute for k as 1.5. That will give me 1 minus 2 into 1.5 is 3 plus, if you just do this, you'll get 6.75. That is equal to 4.75. Up to 2 decimal places, they've told us this time. For a medium of refractive index is a function of wavelength lambda given by this. Okay. Now the refractive index they have given it as a function of lambda. The dispersion at lambda equal to 1 micrometer is how much picosecond per nanometer kilometer. Right. So for this we need to understand how the how we define this dispersion coefficient. So dispersion coefficient in terms of wavelength is given as minus lambda over c d square n by d lambda square. So by knowing this equation we can easily find out what is the dispersion. So what does this coefficient really mean? It basically means that so like I said, if I'm giving a pulse in time, it will get broadened because of dispersion, or it will get broadened, or the time might even reduce, squeezed. So what this dispersion with this d lambda means is the broadening of the pulse, or the width and time of the pulse is equal to d lambda times the spectral width of the pulse times z. That's why we have this nanometer kilometer. So for a given spectral width in nanometers and for a given length of fiber, say z, the pulse will be broadened by so much amount. So that is the idea of this coefficient d lambda, and the equation is given like this. So if I want to find this d lambda, I just have to solve this. So we can go ahead and do it. This is nothing but equal to minus lambda over c d square n by d lambda square. So that is d by d lambda of minus 1 plus t to the 6 lambda, that is equal to minus lambda over c times 6. Right? So lambda is nothing but 10 power minus 6 because it's given to be 1 micrometer, and c is 3 into 10 power 8. So the net will be minus 3, 2s are 6, minus 2 into 10 power. This was minus 6 and this is plus 8, 8 minus 8. Minus 8 minus 6 is minus 14. Okay. If d by d omega of 1 by Vg equal to 0, choose the correct option. So this is just another way of writing dispersion only. So, uh, so this is group velocity dispersion, that is equal to d by d omega of 1 by Vg. Right. So if that is equal to 0, what does that mean? If dispersion is 0, that means all wavelengths travel at the same speed. Okay. Choose the correct statement. For uniaxial material, nx equal to ny equal to nz. So this is definitely false, because for uniaxial material, nx will be equal to ny, will be not be equal to nz. So at least one optical axis will have one axis will have a different refractive index. Biaxial material, none of them will be equal. For isotropic material, nx plus equal to, yes, so this is true. And for non-isotropic, again, all these two cases are non-isotropic case. So yeah, these need not be equal. A material XYZ has Nx equal to Ny equal to 2.5 and Nz equal to 2.4 at 1200 nanometer wavelength. So what is the thickness of the quaternary wave plate in micrometers? Right. So it's an anisotropic medium, as we can see, because the refractive index in all the directions are not the same. So for such a medium, what happens is, as the light propagates through the medium, the polarization of the light keeps on changing. So the polarization keeps on changing, and this change in polarization has a time period. So, or has a period. So it will periodically change the polarization and then come back to its original polarization after it has traveled a certain thickness. So this, after some number of micrometers, it will come back to its original polarization. So quarter wave plate is when it has reached 1/4 of this time period, 1/4 of this time period, or 1/4 of this period, not time period, it's a period. So after a particular length, it will come back to the same polarization. So what is this length? So this length is nothing but lambda over n, like we can say ny or nx, both are same only, ny minus nz. So this is the period. So for a quarter wave plate, we take a 1/4 of the period. So by substituting in this, we'll get a number somewhere around 3 micrometers. Okay. For half wave plate is just twice of this, so 6 micrometers. So what will happen after 12 micrometers? It will come back to the same polarization state, light. Choose the correct statement. D is, so the displacement field is parallel to electric field for extraordinary wave or for ordinary wave. So this is true. So it's by definition of ordinary wave, D is parallel to E for ordinary wave. Okay. So now they have given us the propagation constant K equal to beta minus I alpha. The graph best represents intensity versus distance is. So right. So the real part of propagation constant tells us, it basically tells so this is the oscillating part, right? So if when I write e power minus I k x, then this beta will I'll just expand it. E power minus I beta x into e power plus I square is minus 1 minus, so there is already a minus here. I square is minus 1, so that minus 1 is, so this will become plus alpha x, correct? Yes, right. So yeah, so this will contribute to the phase, or it will be the oscillating part of the signal or of the light wave, and this will contribute to the amplitude. So this will so when I'm writing electric field, E is nothing but E naught. In this case, it will be E naught e power alpha x into e power minus I beta x. So this term will actually lead to amplification of E naught. So for very high x, or in this case r, I should have written r. So for very large values of r, this term will blow up, right? Because there is no negative sign here. So it should blow up like here. And yeah, so so this alpha is actually called as the attenuation coefficient. But however, since there's a negative sign here, instead of attenuation, it is acting as a gain. So there will be a gain. So option C is correct. Right? C is correct. XY material group velocity versus wavelength graph given below. Choose the correct dispersion graph for this material. Right. So what is dispersion? Dispersion is correct. We have just seen it here, right?